Namaste, my friend, and welcome back to NEET Chemistry with Typical Monk. This is Class 6, the second step in our bonding journey. Last time, Lewis dots and sp³d gave us the shapes of molecules. But a shape is only a picture. Today we ask the deeper question: why is methane a perfect tetrahedron? Why is a double bond both stronger and more restless than a single one? For this, we need Valence Bond Theory and his beautiful idea called hybridisation. Sarah once told me she could draw the shapes but never felt she understood them. That changed the day she saw the orbitals themselves mixing. Today, one idea at a time, we watch orbitals mix. Take a slow breath. Let us begin. So what will you carry home from today's class? First, Valence Bond Theory and orbital overlap. The idea that a bond is simply two orbitals overlapping and sharing their electrons. Second, the sigma bond and the pi bond. Head-on overlap versus sideways overlap and why one is stronger than the other. Third, hybridization itself, sp, sp², sp³, sp³d² and the shape each one gives. Fourth, resonance and delocalization. Why some molecules, like carbonate and ozone, refuse to sit still in a single structure. And fifth, the NEET drills. Assertion and reason. Match the column and counting sigma and pi bonds. So everything you learn today, you can also score with. Ready? One idea at a time. Let us begin with the simplest question of all. What exactly is a bond? Valence Bond Theory gives a lovely answer. A covalent bond forms when two half-filled atomic orbitals, one from each atom, come close and overlap, sharing the two electrons between them. The shared pair now sits in the region between the two nuclei held by both. And here is the key line. The greater the overlap, the stronger the bond. More overlap means the electrons are pulled harder by both nuclei. This overlap lowers the energy of the whole system. The two atoms slide together until attraction and repulsion balance, and there they settle at a fixed bond length with a fixed bond energy. That balance point is the bond. Valence Bond Theory explains beautifully why bonds have direction and strength. But when David tried to explain methane with plain s and p orbitals, the angles came out wrong. To fix that, the theory needs one more idea: hybridization. Let us meet it now. Look carefully at this diagram, because it is the heart of today's class. Hybridization is this: the atomic orbitals on the central atom mix together into a set of new, equal orbitals called hybrid orbitals, all of the same energy, pointing exactly at the shape the molecule wants. The first case, sp1, orbitals mixes with one p orbital to give two hybrid orbitals, pointing in opposite directions. That is linear, with a bond angle of 180 degrees, as in beryllium chloride. Next, sp2, one s mixes with two p orbitals to give three hybrid orbitals in a flat triangle. That is trigonoplanar, with a bond angle of 120 degrees, as in boron trifluoride. And third, sp3. One s mixes with all three p orbitals to give four hybrid orbitals pointing to the corners of a tetrahedron. That is tetrahedral, with the famous angle of 109.5 degrees, as in methane. Notice how the number of orbitals mixed always equals the number of hybrids you get. Now that orbitals overlap, let us ask, in how many ways can they overlap? There are two, and NEET loves to test whether you can tell them apart. The first is the sigma bond. Here the orbitals overlap head-on, end-to-end, straight along the line joining the two nuclei. This head-on overlap is the largest possible, so the sigma bond is the strongest kind of covalent bond. The second is the pi bond. Here, two parallel p orbitals overlap sideways, forming clouds above and below the bond axis. This sideways overlap is smaller, so the pi bond is weaker than the sigma bond. Now put them together. A single bond is just one sigma bond. A double bond is one sigma plus one pi. And a triple bond is one sigma plus two pi. Count them like that every time. And here is the golden rule that saves you in the exam. The very first bond between any two atoms is always a sigma bond. pi bonds only ever come on top of an existing sigma, so there can never be a pi bond without a sigma beneath it. Here is the trick that turns hybridization into something you can count in seconds. The steric number. It equals the number of sigma bonds on the central atom plus the number of lone pairs on it. That single number tells you the hybridization directly, no guessing. Steric number 2 gives sp³ hybridization, linear, 180 degrees. Think beryllium chloride or the carbon in carbon dioxide. Steric number 3 gives sp², trigonal planar, 120 degrees. Think boron trifluoride or each carbon in ethene. Steric number 4 gives sp³ tetrahedral, 109.5 degrees. Think methane and also ammonia, where one of the 4 is a lone pair. And beyond the octet, steric number 5 gives sp³d, as in phosphorus pentachloride, and steric number 6 gives sp³d², as in sulfur hexafluoride. Count the domains, name the hybridization. That is the whole game. Sometimes one single structure simply cannot describe a molecule honestly. The carbonate ion is the classic example. Draw carbonate. 1 carbon in the middle, 3 oxygens around it. One of those oxygens is joined by a double bond, the other 2 by single bonds carrying the negative charges. But here is the puzzle. Which oxygen gets the double bond? There is no reason to prefer any one of them. So we draw 3 equivalent structures, called canonical forms, with the double bond on a different oxygen each time. None of these 3 is the real molecule, each is only a partial sketch. The true carbonate ion is the resonance hybrid, a single real molecule in which the pi electrons are spread evenly over all 3 oxygens. As a result, all 3 carbon to oxygen bonds are exactly equal, each a blend of single and double, with a bond order of 1.33. And this spreading out is not just tidy bookkeeping. Delocalization actually lowers the energy. The real hybrid is more stable than any single canonical form could ever be. Lisa remembers it this way. The same story explains ozone, with its 2 equal oxygen to oxygen bonds. Now set up straight. These 5 lines are what NEET actually asks year after year. 1. Versus sp²d. This alone answers a huge share of bonding questions. 2. More S character means a shorter bond and a larger bond angle. That is why the angle falls from 180 degrees in sp³ to 120 in sp² to 109.5 in sp³. D. A sigma bond is stronger than a pi bond, and the very first bond between 2 atoms is always the sigma. 4. Count bonds carefully. A single bond is 1 sigma, a double bond is 1 sigma and 1 pi. A triple bond is 1 sigma and 2 pi. 5. Resonance lowers the energy and equalizes the bonds. In carbonate, all 3 carbon to oxygen bonds are identical with a bond order of 1.33. Let us drill the neat way. Remember the 4 options. Option A, both statements true and the reason explains the assertion. Option B, both true but the reason does not explain. Option C, assertion true, reason false. Option D. Assertion false. Reason true. First one. Assertion. A bond made from an sp hybrid orbital is shorter than one made from an sp3 orbital. Reason. More s character pulls the shared electrons closer to the nucleus. Check each on its own. Is the assertion true? Yes, sp bonds are shorter. Is the reason true? Yes, more s character means the electrons hug the nucleus more tightly, shrinking the bond. And does the reason explain the assertion? Perfectly. Both true. Reason explains. Option A. Second one. Assertion. A pi bond is weaker than a sigma bond. Reason. A pi bond is the first bond formed between two atoms. The assertion is true. Pi is indeed weaker. But the reason is false. It is the sigma bond that forms first, never the pi. So assertion true. Reason false. Option C. This is the trap John fell for, mixing up which bond comes first. Third one. Assertion. All three carbon to oxygen bonds in the carbonate ion are equal. Reason. The carbonate ion is a resonance hybrid. The assertion is true. The bonds are identical. The reason is true. Carbonate truly is a resonance hybrid. And the resonance is exactly why the bonds are equal. So the reason explains the assertion. Both true. Reason explains. Option A. A quick match now. Say each answer aloud before I reveal it. Beryllium chloride, sp hybridized and therefore linear. 2 domains, 180 degrees. Boron trifluoride, sp2 hybridized and therefore trigonoplanar. 3 domains, 120 degrees. Methane, sp3 hybridized and therefore tetrahedral. 4 domains, 109.5 degrees. And phosphorus pentachloride, sp3d hybridized and therefore trigonobipyramidal. 5 domains. If all 4 came to you before the reveal, hybridization is becoming yours. Here is a favorite NEET format. I will read some statements. You silently count how many are correct. Statement 1. A carbon-to-carbon triple bond has 1 sigma bond and 2 pi bonds. Hold your verdict. Statement 2. A pi bond is stronger than a sigma bond. Think about which overlap is larger before you answer. Statement 3. An sp hybrid orbital has more s character than an sp3 orbital. No, how many are correct? 2 statements, the first and the third. A triple bond truly is 1 sigma and 2 pi, and an sp orbital truly is 1/2 character against only 1/4 in sp3. But the second one falls. The sigma bond is the stronger one, not the pi, because head-on overlap always beats sideways overlap. 2 correct, 1 and 3. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. Every bond inside a double or triple bond is a separate sigma bond. It feels natural to just count lines and call them all the same. David believed this for months. But here is the truth. Only the first bond between 2 atoms is a sigma. The extra ones are pi. So a double bond is 1 sigma and 1 pi, and a triple bond is 1 sigma and 2 pi. Never O sigma. Myth 2. In phosphorus pentachloride, all 5 phosphorus to chlorine bonds are identical. The truth, they are not. In this sp3d trigonal bipyramidal shape, the 2 axial bonds standing straight up and down are longer and weaker than the 3 equatorial bonds spread around the middle. That unequal pair is a favorite NEET catch. Do not let it be the one that costs you. Time to test yourself, rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. What is the hybridization of carbon in methane? 4 bonds, no lone pairs, steric number 4, sp3. Question 2. How many sigma and pi bonds are in a triple bond? 1 sigma and 2 pi. Question 3. Which hybridization gives the largest bond angle, C, P, C, P2 or sp3? The most S character wins, sp, at 180 degrees. Question 4. What is the hybridization of sulfur in sulfur hexafluoride? 6 bonds, steric number 6. sp3-2-2. And question 5, the thinker. What is the carbon to oxygen bond order in the carbonate ion? 4 bonds worth of bonding spread over 3 positions, a bond order of 1.33. If you caught that fraction, you have truly understood today's class. Let us gather the whole class in one slow breath. A covalent bond is the overlap of 2 half-filled orbitals, and the more they overlap, the stronger the bond. A sigma bond is head-on and strong, a pi bond is sideways and weaker, and the very first bond is always a sigma. Hybridization follows the static number sp², sp³, sp³d, and sp³d² for 2 through 6 domains. More S character means a shorter bond and a larger angle, 180 degrees for sp, 120 for sp², 109.5 for sp³. And resonance spreads the pi electrons, equalizes the bonds, and lowers the energy, just as in the carbonate ion. And next class, the third and final step of bonding, molecular orbital theory, where electrons belong to the whole molecule, and hydrogen bonding, the gentle force behind water itself. Do not miss it. And so, my friend, we have taken the second step. Lewis dots gave us the shapes, and today, hybridization gave us the reason behind them. Every tetrahedron, every flat triangle, every linear molecule you will ever meet, you can now explain, not just memorize. Sarah, David, Lisa, and John all reached the same clarity by watching the orbitals mix, one idea at a time. Be patient with yourself. Tonight, revise just this static number to hybridization. Sigma before pi, and resonance lowers energy. Say it once, slowly, and it is yours. One idea at a time, you will crack NEET. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in molecular orbital theory.